All right, so we've just seen this best approximation property of the finite element method, and hopefully it gives you a little insight into how the method works in picking solutions from the space that we have chosen for it. In this segment, I'm going to derive another result that is sometimes called the equivalent of the Pythagorean theorem for this particular problem that we're working with. And it has a nice consequence that is useful to note when one is actually looking at numerical solutions and comparing with exact solutions. Okay, so so the title of this segment is the Pythagorean Theorem, right? And it's really in quotes because it's similar to that, but it's not the original Pythagorean theorem. Okay, right. Here is the theorem first of all. This theorem is really a corollary of the fact of consistency, but okay, so let me state it as a corollary. Okay, and the corollary is this. It is that, right, if we consider the energy norm of the exact solution, okay, this is equal to the energy norm of UH, comma UH plus the energy norm of the error, okay, for a specific kind of problem. Okay, this holds for a problem where SH equals VH. Now, if you're wondering what that means, it simply means that our Dirichlet boundary conditions for this particular problem are homogeneous ones. Okay, so any place that we specify the Dirichlet boundary condition, we are saying that that Dirichlet boundary condition is 0. Okay, all right. So what this means is Dirichlet boundary conditions are homogeneous. Okay. All right. And you note that this actually holds for the Dirichlet-Neumann problem. Okay. In fact, something that we often remarked upon during our development of the finite element method for that particular problem was that, well, yes, if we have the left end of the bar fixed, then SH and WH are the same, right? Sorry, SH and VH are the same, right? Or alternately, little UH and WH satisfy the same conditions, right? The same boundary conditions. Okay, it is for this case that it holds. So proof. Okay, so let's, in order to start looking at this, let us consider here, right, let us consider the following. For this setting, we have UH minus U equals E, right? That's our definition of the error, right? This is the error in the finite element solution. And from this, we can therefore write that U equals UH minus E. Therefore, when we consider on the left hand side the energy norm of the exact solution, we see of course we see this, but now just as we did in the previous segment, we can expand out the term on the right hand side by just using the fact of bilinearity. all right, and this gives us a comma minus a comma e minus a comma minus plus a comma e. All right. Okay, and then as before, we recognize that the second and third terms are the same because of the fact of what? Fact of symmetry, right? The symmetry of the bilinear form, right? So that lets us write it as a comma minus twice a comma e plus a comma e. Okay, but now if you look at the condition in the statement of the corollary, you should be able to see something about the second term there. You should be able to say something about the second term. What can you say? This is equal to twice a of WH comma E, because the spaces SH and VH are the same, right? So UH is the same as WH, right? UH is a WH. It is indeed a weighting function. Okay? And this therefore is equal to 0 by consistency. Okay? And there we have it, right? What we are left with is the result we set out to prove. Okay? This is A, the energy norm of the finite element solution, plus the energy norm of the error. Okay? This holds, of course, for problems where the Dirichlet boundary conditions are homogeneous. Right? So it's a useful thing to note. In some sense, this looks just like the Pythagorean theorem, recognizing that the energy norm involves a square. So it's like saying that if we use this bilinear form to define a more generalized version of an inner product, right? It is indeed an inner product, but we can use it to define a more generalized notion of a square, right, of two functions, right? Then this generalized notion of the square of functions tells us that in as much as we admit this to represent a square, we're saying something to the effect of u square equals UH square plus E square. Okay? Right? So that is why we call it a Pythagorean theorem. What good is this? Okay. A corollary of that one. Okay. So let's call this corollary. Maybe I should call this corollary 2 and I call that corollary 1. So let me do that. Let me go back now and call this one this corollary 1. Okay. Okay. Corollary 2. It says that corollary 2 is actually trivial. Let me state it. The corollary 2 says the finite element solution, okay, underestimates the energy norm of the solution. Well, let me not say of the solution. Let me say the energy norm of the problem. Proof is a single step. from corollary 1, we see that A u comma u equals A comma plus A comma E. Now, because of the nature of this bilinear form and the fact that it leads to an energy norm when we use the same function in both slots, we know that this is greater than or equal to 0, and so is this, right? This is a fact that we've remarked upon in the previous segment. All right, what this implies for us then is that if we drop the last term, what we get for the right hand side is that A of comma the energy norm of the finite element solution, is lesser than or equal to the energy norm of the exact solution. Okay, and this is what we mean by saying that the finite element solution underestimates the energy norm, right, of the problem. The exact energy norm of the problem is what we have on the right hand side here. Okay, when we get the finite element solution and we go back and compute the energy norm, which is what we have on the left hand side, we will be computing an energy norm which is less than that of the exact solution. Why does this matter? Well, it is, as all norms do, this is a particular way in which to get some sense of, another sense of control over the solution. What is the solution doing? How big is it? Well, you can compute its energy norm. It turns out that the energy norm that we get from the finite element solution is not as big as the energy norm of the exact solution. Where else might it matter in a more physical sense? If you're solving a problem in linear elasticity, for instance, where the energy norm as written out here actually has physical meaning, and it in fact corresponds to what? Corresponds to the strain energy, right? What it says is that if you had the exact solution available to you and you were to go ahead and compute the strain energy of the exact solution and compare the strain energy of your finite element solution, what you ought to see is that the finite element solution actually underestimates that strain energy, right? It gives you a smaller strain energy. Okay, so that's a particular result of this method. Okay, we're actually going to end this segment here. It's a shorter segment, but we are getting prepared for the main results of our analysis of the finite element method.